All right, so today's lesson is a lesson about light production and a little bit about how we know what we know about the atom itself in terms of what it looks like in three-dimensional space. So in an effort to talk about that, you're going to definitely not need your cellies or your chromies. You're just going to need to pay attention and write some stuff down. So here we go. Here are some things that we do know for sure. We know that if you heat certain substances, they will start to glow. And when they glow, they will give off specific colors. You may have witnessed this, I don't know, in the summer when you look at the fireworks during the 4th of July, right? What happens is that when you see the firework that produces red, it might be using like some form of sodium metal as part of its contents. If it is a firework that produces bright white, it might be magnesium that it's used as part of its contents. So as we heat things up and they tend to glow, they will give off very specific lights, or colors of light rather. Every element has its own unique light that it gives off. We call that the emission spectrum. Now, what this is up here is the top one is the visible light spectrum. Yes, sir?
What's the rarest element? Do you know?
Huh?
Do you know what's the rarest element?
The rarest elements technically are the ones that are man-made. They're the ones in the bottom couple rows of your periodic table because they are really unstable and they don't exist until it's like you make them and then they break apart. Now, with that in mind, with this in mind, so visible light spectrum, gentlemen, so visible light spectrum, right, is the colors red, orange, yellow, green, blue, all the things, right, and purple. But down here, the next row is sodium, and the next row is hydrogen, and the next row is calcium, and the next row is mercury. And in your note packets, when you're looking at that, you don't necessarily see the colors, but you do see these bands or these lines, right? On my notes up here, or on my screen, the bands that are shown are specific colors. So sodium will give off, when it's heated, it will give off a band that is orangey yellow, or I'm sorry, like this reddish orange here. It will give off a band that is yellowish here. It will give off a band that is like yellowish orange here, or something like that, and it will give off a band that is sort of bluish here. Okay? And when it gives off those colors in terms of bands, right, that's unique to sodium. No other element gives off those very specific bands and those combinations at the same time. Hydrogen gives off 4 other bands. Calcium gives off a lot of other bands. And mercury gives off a very specific amount of bands. Okay? These emission spectrum, are the fingerprint for each element. And so how we know, for example, what stars are made up of is when we take in starlight energy from outer space in in specific types of telescopes. One of the things that those telescopes do is they look for these bands of a light spectrum, and they can identify the elements that are present. So if a star has sodium present in it, it would see a lot of bands that look just like this. Does that kind of make sense? I mean, it's kind of crazy that that's how they do it, but that's sort of how they do it. And then, a long time ago, the model of the atom that we worked with was essentially like a bag of marbles, right? So like long time ago, like way back in philosopher time, people were like, atoms, or all stuff is made up of these tiny spherical objects that we're just going to call matter, and we call them atoms and things like that. Okay, but fast forward to like the late 1800s, early 1900s, and we actually did some experimentation to identify what atoms look like. And one of the people that did that was a gentleman named Niels Bohr. He basically said that electrons are organized into energy levels, and the inner energy levels have lower energy and the outer energy levels have higher energy. it's kind of like a hotel sort of situation. So when you go to the hotel and you check into the hotel, the first floor is generally where the lobby is. And when you check into the lobby, like that's the nucleus of the hotel. Okay. If you are told that you are assigned room 204, for example, it means that you're on the second floor and you're like four doors down from the exit. Okay. Does that make sense? If your buddy is assigned to like room 709, they're on the seventh floor and they're like 9 doors down from the exit. Does that make sense? So far, so good? If you were to drop something like a water balloon out of your balcony off of the second floor, it would clearly go to the ground and it would splat and make a mess with a very specific amount of force. But if your buddy was to drop the same size water balloon off of the balcony on the seventh floor, it would hit the ground with a lot more force. Does that make sense? So that's how I like to think about Niels Bohr's model of the atom. He basically said that electrons are assigned to an energy level and they have to stay there. And the only way that they can move to an energy level is if they get excited. So if, for example, an electron was on the first energy level, we would call this its ground state. Its initial assigned room. If an electron absorbed a lot of energy for whatever reason and it jumped up to this level, like this, we would refer to it as its excited state. Now, an electron can only exist in its excited state for a little bit of time, and after that, it has to go back to its ground state. We're going to kind of talk about that in a minute. Niels Bohr's model is not correct. It just doesn't really get to the crux of what an atom actually looks like, but we use it a lot of times to demonstrate the idea of where electrons are located and that they can move amongst different energy levels. One of the things that we can use this model for is that atoms can move to higher energy levels by absorbing energies. So if an atom absorbs a photon of energy, so if an atom absorbs a photon of energy, like this, the electron in its ground state can become excited and move up to another energy level. So in this instance, what happens is that as atoms absorb energy, the electrons in the atoms also absorb the energy, and they move from their ground state to their excited state. Now, the issue is that the electron can't stay in its excited state. That's actually not practical or stable. Like, if you eat a bunch of sugar, you get really excited, but you don't stay in that excited state for very long. You eventually crash and take a nap on the couch, right? And that's basically what happens with electrons. So electrons that are in their excited state fall back down to their ground state, and when they fall back down to their ground state, they happen to emit the same amount of energy that they originally absorbed. So I needed so they give off the same amount of energy that they absorb. So energy is released in the form of light. So if we excite an electron jumps to its higher energy level, its excited state, that electron will eventually come back down to its ground state and give off the energy it absorbed. And that energy is detected by our eyes as light, different colors of light. So let's talk about how that would look if we were an atom. So we're going to take a look at a specific light color. We're going to look at red light. So now, red light is in a part of the visible light spectrum that has long wavelengths. It has low frequency. And it has low energy.
That one laser pointers is colored red.
They use what now?
The color red.
No, kind of, sort of. Red is a pretty easy one to make. We can make them different colors. We just need different metals. Now, in this instance, if I have my electron at its ground state, right, and I add a photon of energy where the wavelength is like really far apart and the frequency is really, really low, that electron will really only jump up a short distance. So it'll be a short jump to its excited state. Because it absorbed low energy. So it absorbed low energy. And consequently, if it absorbs low energy, it can only give off low energy. So we can't give off more energy than we absorb. So that would look something like this. Did I go too fast? Okay. So if the electron is here and it drops back down to here, it's going to only be able to give off the same amount of energy that it put in, which looks like that. And so that energy that it released is given off in the form of red light. And so the electron went from its ground state to its excited state. And it wasn't a very big jump, but it still went up to its excited state and then came back down to its ground state in the form of red light. Another example of this would be if we observed purple light. So what we know about purple light is, yep, it has a short wavelength. It has a high frequency. Yep. And high energy.
So, like, if you were to have purple lights, like a purple light bulb, would it run out quicker than a white light bulb?
The question is, if I had a high short wavelength, high frequency, high energy light bulb, would it run out faster than a low energy light bulb? And the answer to that question is most likely not.
No.
Okay. It's just that it's going to require more energy to give the light off. So it might require more energy to work, but it won't necessarily run out faster. Now, what this would look like potentially is if I was to draw my wave coming in, 3, 4, 5, 6. Okay, this electron will jump up to, say, this energy level here. So we're going to say that this is a large jump. Because the electron absorbed high energy. Now, again, it went from its ground state to its excited state, but now that it's in its excited state, it has to go back down to its ground state. So the same electron is up here in its excited state. I better put it in the right spot. Okay, and it's going to come down to its ground state, and when it does that, it's going to give off the same amount of energy. Okay, so it's going to give off energy in the form of purple light. Now, these jumps to higher energy levels and fall back down from higher energy levels to the ground state are what give the atom or atoms their very specific electron emission spectrum. So what that means is that if I have an atom and I have it absorb different amounts of energy, right? I can have an electron jump from, say, here down to here. I can have an electron jump from, say, here down to here. And I can have an electron fall from, say, here down to here. And what that will look like will be based on the amount of energy that the electron has absorbed. So the electron that is furthest away has the highest energy, and it might look like this. The electron that is the middlest amount of energy might look like that. And the electron that has absorbed the least amount of energy might look like this. And so each of these absorptions and releases of energy correlates to a line on the emission spectrum of that particular atom. Does that make sense? Maybe. Hopefully. Sort of, kind of. So now, we have discussed that the Bohr model is good for using as a model to explain how the atom kind of sort of works. But we've also mentioned that it's not a great representation of what an atom actually looks like. So we're going to talk a little bit about what atoms actually look like going forward. Now, so shortly after Bohr came up with his model of the atom, there was more research done, and I want to say within 2 to 5 years, a gentleman by the name of Louis de Broglie did some experimentation and found out that electrons, like light, can diffract and they can produce interference. So de Broglie, who had great hair and was a decent looking guy, he's a decent looking guy, not going to lie. And he had excellent hair. He postulated or theorized that electrons, which we're saying are particles, behave like waves. So if light can behave like a particle, then electrons can behave like a wave, is what he basically said. And then, so that's how that's why the photoelectric effect is really important in our understanding of what atoms are. And then there was a gentleman with the last name of Heisenberg, and he gave us something that we call Heisenberg's uncertainty principle. And Heisenberg's uncertainty principle basically says that, listen, you can know either the exact location of an electron or you can know its speed, but you cannot know both at the exact same time. I guess if you think about it like this, if you're driving in a car and somebody is watching you, they can say, hey, you're right there. But they can't necessarily say at that particular point in time when you pause the world how fast they were going. And that's how we feel about electrons, is we can know either A, where they're going to be, or B, how fast they're going to go. And that's basically what we understand about that. That's him. There's a better picture with his hair, man.
Yeah, I was going to say his hair is not looking too
Now, the quantum, which brings us up to the quantum model. And the quantum model, this picture right up here on the board, the picture right here that we're looking at, makes it look like around the nucleus of this atom, there's like a bajillion electrons. And that's not true. Every single one of those points around the nucleus of the atom is the potential probability / location as to where an electron might be. Think about it like this. I can predict that at 3 a.m., the vast majority of you are in the part of your domicile that you refer to as your bedroom. Isn't it, though? Domicile is a funny word to say. But what I'm getting at here is that I can predict that you might be in your bedroom, but I can't predict exactly where you are in your bedroom. And the area that an electron moves around the nucleus of the atom is very similar to that. We can say that the electron has a bedroom to sort of exist in, but we don't know exactly where it is. But what's important and what I like about this particular diagram is the density of dots, the density of potential places where the electron could be, is really, really mostly packed around the nucleus. And the further away from the nucleus that the electron potentials are, right, the less of them that are present. Do you kind of... Pardon?
Is it like I was saying? It's more sparse.
Yes, it is more sparse as you go further out.
I'm like, wait, is it sparse or sparse?
It is more sparse. Now, this allows us to talk about something that we refer to as an orbital, which is a three-dimensional region around the nucleus of an atom where we could expect to find the actual atom itself, or the actual electron itself. That region is, like I said, in three dimensions, and as a result of that, it gives us sort of a general idea as to where the electron could be. So you need to know what an orbital is, which is the thing I just highlighted. That's the definition. You probably need to write it down. It's this 3D space around the nucleus of an atom where electron might be hanging out. And the other thing about the quantum model is that we borrowed some stuff from Bohr and we borrowed some stuff from other people. But what I really want to make you understand is that these points here are the answers to math equations, to math problems. So instead of holding the model of an atom in our hand, we're basically saying we did a lot of math and this is about where an electron can be. Now, atoms are like ogres. Atoms are like ogres.
Oh, yeah,
They have layers. Remember from Shrek?
yeah.
Right?
That's a
which are like onions because they have layers. See what I did there? All right, so we can say for the scope of this class that all atoms have 7 energy levels or shells. Okay. The further away from the nucleus that an energy level is, the more energy the electron will have.
But further?
The further. So if this is my nucleus and my electron is like here, it's going to have, let's say, X amount of energy. But if it is 1, 2, 3, 4, 5, 6, 7, it's going to be like 7 times X the amount of energy. Okay? Kind of. Not really, but kind of. So what that brings us to is that every energy level has different sublevels or shapes that exist inside of them. It's kind of like parts of a video game, like old school video games like Super Mario Brothers, where in order to beat level 1, you have to beat 1-1 and 1-2 and 1-3 and 1-4, and that beats level 1. And then you have to do 2-1 and 2-2. So that's kind of what it's like in my head, but I'm old, so whatever. So every energy level has different sublevels, and the different sublevels are kind of shapes that we can describe. One of the shapes is the S shape, which is basically spherical, which I can't spell. That's probably wrong. But it's a sphere, and I don't know how to draw a sphere, so I'm just going to draw a circle. Another one is dumbbell shaped, which is the P sublevel. And it kind of looks like this. And I'm drawing it in 3 different directions in an effort to kind of like, we'll hit this harder a little bit. And another one, the D is like clover leaf shaped. And it kind of looks like something like that. And then F is 8-lobed. And I'm not even going to try to draw it because that's crazy talk. And I'm going to show you pictures of what these actually look like in a minute. But for now, you should know that every energy level potentially has an S sublevel, a P sublevel, a D sublevel, and an F sublevel. So how do we describe these? Well, their orientation, when we talk about that, we're talking about their orientation in 3-dimensional space.
Can you go back up? Or, yeah.
So their orientation is in 3-dimensional space is what we're talking about. And so if something is considered to be spherical, well, there's really only one way to look at it, spherical, so it has one orientation. The P sublevel has 3 orientations. Like the the X plane, the Y plane, and the Z plane, like in geometry. Those are the 3 orientations in space that it has. It's not? Oh, is it A and T? All right, well.
No, I thought it was like
3D stuff, yeah.
Yeah, it's like.
Yeah. And then the D has got 5 orientations. And the F has 7 orientations. Now, here's a picture of what that might look like. So here's my S sublevel. It's a sphere, and there's one version of a sphere that you can have. You don't have this, but I'm just showing you. Here's the P sublevel. See how they exist on the x-axis and the y-axis and the z-axis? Then here's the d sublevel, which is combinations of the x and the y, the z and the y, the z and the x. And then here's the f sublevel, which gets way more complicated. So we just kind of pretend, we just talk about it a little bit and then we move on. And then every orbital in a sublevel can hold 2 electrons, 1, 2. But if we're talking about it in terms of like their bedroom, right? If I have 2 electrons that are both what charge? What charge? What is the charge of an electron? Negative, right? If I take 2 electrons that are negative and I put them in the same space, they're going to do what? Repel, right? So what electrons actually do is they change how they spin in that space. So instead of spinning in the same direction like this and repelling, what they do is they spin in opposite directions like this, and they are able to exist in the same space. Is this hurting your head yet? Don't try it. You'll break yourself. Now, see, you're broken. You're broken. You're broken. So we'll talk more about the spin and the importance of it on Monday. So let's summarize some of this business. The first energy level has one shape or one sublevel, which is the S sublevel. And it has one orientation, and it can hold 2 electrons. The second energy level can have the S and the P subshells or sublevels, and it can have 2 orientations. S has 1, P has 3, so that's 4. And it can hold 8 possible electrons. The third sublevel can have the S, the P, and the D subshells. So we have S as 1 orientation, P is 3 orientations, D has 5 orientations for a total of 9. And that will hold potentially 18 electrons. And then lastly, the fourth, the fifth, the sixth, the seventh energy levels can have an S, a P, a D, and an F. The S again can hold 1, the P can hold 3, the D can hold 5, and the F can hold 7, for a grand total of 16. And that can hold a potential for 32 total electrons. So, what I want to show you now, as you are thinking about what your homework is going to be, your homework is going to be worksheet number 4. 4. 1, 2, 3, 4. And I want to show you this situation here. It's a brief video that you can listen to as or watch as you're kind of working on the homework for the last 5 minutes of class. But it's what an atom really looks like. Just stay sitting. Stay sitting.
Would this be 5 minus 2? I saw what he was saying.
Come on, Jack. Oh boy. Got smoked. He got smoked. No. He's done. Oh my god. No, you're done. I saw my phone. No, you're done. I saw my phone. Make a move. Make a move. What are you doing? Make a move. Let's go work that out. Yeah. Really? For real. Come on, Jack. We should try to make a move. I smoked a Justin now.
So that was our lesson for today. Hope you, if you have any questions, touch base with your instructor and have a good day.